So welcome everyone to this week's seminar. So today's speaker is Adam Falkowski from Orsay. Adam is a faculty member there, and before he got his PhD a few years back and has been postdoc at decays, CERN and Rutgers, and he has been working on a variety of topics in beyond standard model physics, and specifically he focused on effective field theories recently, and today he will be talking about constraints on new physics from nuclear beta transitions. So please, Adam.
Thank you very much. I'm very happy to be in Sydney. So I've never been to Australia and in body, so that's I'm still dreaming of this journey. Hopefully it will happen in better times. So at least here I am virtually, and also apologies if I sound incomprehensible. Yeah, it's 7 a.m. for me. That's also the earliest seminar I've ever given. So if there is some lapses of logic, yeah, this is certainly there must be a fault of the early hour. So I will talk about these nuclear beta transitions. This is like this is a topic that is less discussed probably among particle physicists, because it belongs somehow to a very low energy domain, yeah, where it different older kind of physics. But nevertheless, it is actually quite important for particle physics, yeah, both from the standard model point of view and from the point of view of physics beyond the standard model. And here I will be talking about constraints on actually both standard model physics and new physics beyond the standard model from variety of beta transitions. And this will be based on the paper that appeared last year on Archive with Martin Gonzalez and Oscar Navillat. And also there is still some work and has been done since, yeah, but mostly about updating the global fits that because of new experimental data that are still incoming. So, okay, sorry. So what are the beta decays? So at the quark level, yeah, we have this process here where the up and down, or one of the quarks turns into another quark, or up or down, or the other way around, while emitting a electron and a neutrino. So this is what happens at the most fundamental level of we know. But what we observe, of course, is not the quark transition. What we observe is either a nucleon transition, where neutron turns into a proton, or we observe a really literally thousands of different transition of nuclei, where this is just one example where carbon-14 goes into to nitrogen-14. So in this case, one of the neutrons in the nucleus turns into a proton, and this is so-called beta minus decay. Or we could also have a proton in a nucleus transitioning into a neutron, and then it will be a beta plus decay. So this is what I will be talking about for the next hour. This is the processes. But what I find going down to the physics and the standard, the electroweak scale through the physics, we can actually decay and translate them into some parameters of models at the very high scale, or also the parameters of the standard model. And this is I will try to explain how this is done, a little bit of the theory behind. In one of the previous slides, yeah, is that this they regard the transition between the quarks and leptons, so they probe interactions between the quarks and leptons, so you could describe it in a particular model, or the standard model, or some extension thereof. But what I'm going to discuss here is a little bit different approach, yeah, where we will be describing this this transition using the language of effective field theory. So without referring to a particular model, but instead trying to develop a framework that encompasses a large number of different distinct models. So let me start this journey through effective field theories, and let's start it with a top-up approach, and starting with the highest scales that we can discuss here. So at this high scales, there is some model that we don't know. We expect that standard model is not the whole story, so there is some fundamental or BSM model, which itself might be an effective theory of something else. But in this model, yeah, we will have several processes that will contribute to the beta decays. So first, we will definitely have the process here that already occurs in the standard model. That's d quarks, and d quark turns into an up quark while emitting a virtual W boson, which turns into a pair of electron and a neutrino. However, in this fundamental model, we can have other non-standard model contributions to beta transitions. So, for example, if there is a partner of a W boson that I call here W prime, you will have the same process but mediated by another heavier particle. Next thing you could have is so-called leptoquarks, which instead of being the currents between the quarks, being mediators between the quark and lepton currents like W or W prime, they are actually mediate interactions between the quark and lepton pairs. Yeah, so they could couple to quark and a lepton, and this could be another source of another contribution to the beta decay. And finally, we could have, for example, W left-right models where they have a left-handed W and right-handed W that mix with each other. And in this case, the W boson, which in the standard model couples only to the left-handed particles, yeah, it could also couple to the right-handed quarks, yeah, which is some phenomenon that is not present in the standard model. So we could have all these different contributions, different particles. Yeah, this is not a exhaustive list, of course, but just some representative examples. But yeah, then we have to go down to lower energies and to energies below this fundamental scale of the fundamental new physics models, to the electroweak energies. And then in the electroweak energies, yeah, all these effects of heavy particles, yeah, they will be encoded in the effective operators that at these energies, they will be invariant under the full standard model gauge symmetry, because above 100 GeV, this gauge symmetry is unbroken. So we have the description should be gauge invariant. Yeah? So there is a large number of different effective operators here that we could write down that will contribute to these beta transitions. And different forms of new physics, yeah, will be encoded, yeah, in a different sort of operators. Yeah, for example, if you have a W prime, you will generate this kind of operator, yeah, which you have two left-handed quarks and two lepton doublets, yeah, that interacting with each other via contact interaction. So something that is not present in the standard model, on the other hand, leptoquarks, yeah, will give you different kind of interactions. So when you integrate out a leptoquark, yeah, you will get typically actually a mixture of different operators of this kind, where you have either tensor or scalar interactions between the lepton and quark currents. Yeah, so the typical model of leptoquarks, it generates a linear combination of two or more of this scalar and tensor operators. And finally, if you have this left-right mixing, yeah, you will generate this operator, yeah, that by itself it doesn't contribute to the quark and to the beta transitions, to interaction between quark and leptons. What it does, it generates, after you put a vacuum expectation value for the Higgs, it will produce a coupling of a W boson to right-handed quarks, and then via this W boson exchange, you will get this new kind of contributions to beta decay. So this is the description of the electroweak scale, yeah. But this again, this is we are at very high energies compared to the scale of beta transitions. So we have to go down this ladder of effective field theories to better understand what is going on. And the next step, yeah, we go down from 100 GeVs to a few GeVs, yeah, where we have to integrate out the W bosons, so the standard model, and also the Higgs boson and the top quark. And then we are left with a theory of quarks, where electroweak symmetry is no longer manifest. And in this case, the effective Lagrangian will have a much simpler form. So as we go down with energy, actually the description here will simplify. Because of this, instead of this large number of operators, yeah, we will have just a much smaller and compact number of operators that are leading the leading contributions to beta transitions. And in this case, you will have only contact interactions. There is no more W boson at this energy. So if we imagine we are at the energies of a 2 GeV, W boson is integrated out. All that's left of the W boson is this kind of interaction, yeah, between the left-handed leptons and left-handed quarks. But again, if you have new physics, yeah, which generates this other operators like scalar or tensor or pseudoscalar, yeah, this will manifest itself at the low energy scales as this contact interactions, yeah, with scalar, pseudoscalar or tensor structure. And finally, there is you can also have the similar kind of vector interaction like in the standard model, but with right-handed instead of left-handed quarks. And then if you want to be completely general, yeah, you can, instead of left-handed neutrinos, you can have right-handed neutrinos involved also in beta decays. We don't know if right-handed neutrinos exist or if they have small enough mass, yeah, to be to participate in beta decays. But if they exist and if they are light, yeah, you could also have this another kind of interaction, yeah, but that is similar as for the left-handed neutrinos, but you just replace the neutrino with an opposite chirality, and of course you have to also replace electron with an opposite chirality in these interactions. So this is the description at the quark level, yeah, and we can always map, yeah, we can always go up and down, yeah, in between this in the energy scale. And if we want to connect this, for example, Smeft Lagrangian, yeah, to this low energy interactions, yeah, we can always write down a map between the two, yeah, how these two are connected. So once you measure this quark level Wilson coefficients, yeah, you can translate them, yeah, into the Smeft with Wilson coefficients by using this map. Yeah, so this is at least in the leading orders, yeah, in the effective theory expansion, yeah, this map is very simple to work out. Yeah, it's just the connection between these parameters is pretty straightforward. But again, we have to make to connect to observables. Yeah, we have to make one more step down in this ladder, because beta transitions, yeah, don't happen with the quark level. They happen at the nucleon level. Yeah? So we have neutrons and protons involved and not quarks. So the next step, yeah, that we have to do, we have to go down to the energies where below the hadronic scales, and then quarks replace the up and down quarks, yeah, with protons and neutrons. And then we're getting the Lagrangian, effective Lagrangian, that was actually already written almost a century ago by T.D. Lee and C.N. Yang. And this was before the birth of the standard model. So they didn't know what is the structure of these interactions that standard model predicts. So because they didn't know, in the spirit of effective theory, before it was fashionable, they just wrote all possible interactions that you can write at the leading order. And again, we have 10 parameters here, yeah, with 10 Wilson coefficients. Here I denote them as CV, CA, CS, CT, and CP, and the plus and minus refers to whether we have a left-handed neutrino or right-handed neutrino. Yeah? So see, the ones with the minus upper index, yeah, refer to the right-handed neutrinos, yeah, and this one are perhaps the more important, yeah, because those involve the left-handed neutrino that is already present in the standard model, and yeah, this. So we have again 10 parameters, yeah, at this level, and this is what connects to experiment in the most straightforward way. However, it is, so we could stop here. So for example, in the Li and Yang, yeah, they stopped at this level. But if you want to have a good understanding of what's going on, the good understanding of physics, then it's actually better to make one more step to yet lower energies. And the reason is the following, yeah, that in the beta transitions, the momentum exchange is very small because of the small mass splittings between the nuclei or nucleons. So typical momentum exchange in the beta transition is of the order of an MeV. And for example, for the neutron decay, when neutron decays into protons, yeah, this is we know it, that the mass difference between the neutron and the proton is of the order of only 1.2 MeV. Yeah? So this is the available energy or momentum for this transition. So if you want to, so the energies or momenta involved are much smaller than the masses of the nucleons. Therefore, we could, instead of using the relativistic description like Li and Yang, we could go to a non-relativistic effective theory and replace protons and neutrons, yeah, with relativistic fields with non-relativistic fields. So this step is this step is done. So what you do here, yeah, is a certain transformation of the level of the fields, yeah, which you can write down in full generality. So you replace this P and N nucleon relativistic fields, yeah, you replace it with what I will denote as psi n, or psi p, or psi n, and this will describe the non-relativistic fields. The field equation for this guy will be Schrödinger equation rather than the Dirac equation. So this is the technical step, yeah. But once you do this, yeah, you will get a effective Lagrangian that is an expansion now in derivatives, but in spatial derivatives. Yeah. So you can write down these each term in this EFT expansion, yeah, will be suppressed by more derivatives, which of course translates by more suppression of by momentum exchange. So when it's that each consecutive term will be less and less important, yeah, for the phenomenology, because the momentum exchange is very small. So if you do this exercise, you will find that this Lagrangian turns into this Lagrangian, which has a smaller number of parameters. So the parameters corresponding to pseudoscalar interactions, they drop out from the non-relativistic, from the leading order non-relativistic Lagrangian. Yeah, they appear at sub-leading order only. And yeah, so this means that pseudoscalar interactions are not relevant at the leading order for the beta decay. You would have to go to sub-leading orders, yeah, to get any effect of the pseudoscalar interaction observable in these transitions. And on the other hand, vector, axial, scalar, and tensor interactions, yeah, they remain in a different non-relativistic form. Yeah, so you have this kind of interactions that look weird to the eye of particle physicists, yeah, because there is no Lorentz symmetry in these interactions, but there is no Lorentz symmetry at the relevant energies. Yeah, that is the Lorentz symmetry is not manifest. Yeah, so that's okay. Then there is another interesting thing that you can see, except for the fact that the pseudoscalar interactions have dropped out. You can see that also at the level of the hadronic or structures, yeah, you get some simplification. Instead of 5 different Lorentz structures in the relativistic Lagrangian, you get only 2 hadronic bilinears that enter in this Lagrangian. Yeah, so either it's a proton dagger neutron or proton dagger neutron with a sigma matrix insertion in between. And those two structures, yeah, maybe if you remember now from primary school talking about beta transitions, they correspond to the two different types of beta transitions, so-called Fermi transitions and Gamow-Teller transitions. Fermi transitions are mediated by this interaction without sigma, and Gamow-Teller transitions are mediated by these interactions with the sigma. So this is once you go to the non-relativistic theory, you're getting the huge simplification. You can actually understand the structure of this interaction. You can understand all this selection rules that you learn in the courses on nuclear physics. Yeah. So all you need to know, yeah, to describe beta transitions at the leading order here, yeah, is this two matrix elements, yeah, of this bilinears between nucleon fields, and it actually is even. It turns out that it's even better. You can prove that this matrix element you can calculate just using group theory, using in the isospin limit. So this is something that you can calculate independently of all this nuclear physics, dirt, and difficult strong interactions. This is just something given by group theory. On the other hand, this Gamow-Teller matrix element is more difficult, so you cannot calculate it from first principles, at least with the current tools. You have to either resort to lattice or to use some try to determine this matrix element from phenomenology, and so this is quite important, maybe in the story, yeah, that will follow. So this will introduce like another nuisance parameter into the global fits, because these matrix elements cannot be calculated, yeah, for heavier nuclei. So this is the Lagrangian, yeah, that I will be talking about in the rest of this talk. So this is I want to determine this 8 parameters of the Lagrangian. I forgot. I skipped one slide because of the early hour. Yeah, but there is you can again match these parameters, yeah, to the quark level parameters. Yeah, and this is the dictionary between the quark level parameters and nucleon level parameters. Yeah, so this epsilon parameters at the quark level, yeah, translate in this big C parameters at the nucleon level, and the exact form of this matching is known. There is, because this matching, yeah, between the quark level and nucleon level involves some non-perturbative physics. Yeah, there is some non-perturbative elements involved in this matching. So, for example, there is this. So there are these nucleon charges GV and GA and GT and GS and GP that enter in this matching. But fortunately, they are quite well known from theory. Yeah? So, for example, this axial charge is known by the 1% level from theory, from the lattice calculation. And from theory, you can prove that this GV is order 1 up to is exactly equal to 1 up to very small corrections that are quadratic in the isospin breaking, so they are negligible. Yeah, so this parameter is 1, and yeah, for this again, you know those with 10% precision, which is good enough. Yeah, because they multiplied new physics parameters. Yeah, so I think 10% precision in this case is good enough. Okay, so this is the formalism, yeah. So I will the rest of the talk, yeah, will be about applications of this formalism to extract the information about high energy physics from this. If there is any questions, you could ask me at this point, and if not, I will go to next step, the next stage of the talk, yeah, which is observables.
I just ask, are you really telling us that lattice gives a better value for GA than experiment?
No, GA. So I will talk about it in a soon, but this is the value for the lattice. Actually, this is the value from flag review. There are more precise
experimental value is much more precise, yeah, at 1.27 something.
Exactly, and the experimental value is more precise, but as I will explain in a moment, experimental value you can use only, I mean, you can measure GA only assuming the standard model is the correct theory. If standard model is it's not the correct theory or not the complete theory, there is physics beyond the standard model, then your measurements, when you think you measure GA, you actually measure a combination of the GA and new physics parameters. And you can actually see it already here, that there will be this new physics parameters, they will enter into the relation between the low energy and high energy parameters. So your measurement might be contaminated by new physics. So this is true what you said, but only when you assume the standard model as the UV completion.
Second comment, if I could. GV approximately 1 was good once. Once you talk at the level of 10 to the minus 4, it's no longer good because the correction from the difference in the up and down masses, even though it's of order that mass difference squared, is a little in excess, GV squared is a little in excess of 10 to the minus 4, roughly 1.2 by 10 to the minus 4. So in testing unitarity, that needs to be taken into account.
Sorry, I stopped hearing you. I don't know if it's my connection or it's your connection, but yeah.
I didn't realize the value of GV squared deviates from 1.
Hello? Yes.
Can you hear now?
So sorry, I didn't hear the last 15 seconds. I don't know. Yeah.
Okay. The value.
Yeah, I hear you now.
The value of GV squared deviates from 1 because of the difference in UD mass by about 1.2 10 to the minus 4, which starts to be significant now that the test of unitarity is getting down to the 10 to the minus 4 level. So it's no longer good enough to say that GV is approximately 1.
Okay. Yeah. So this is taken into account, but currently, so there is also one more element, in this matching, which is this delta, this radiative corrections,
It's not a radiative correction. This comes from the non-perturbative structure of the nucleon because the U and D masses are different. So it's according to Adamala Gatto, it's of order the mass difference squared.
Okay, I lost you again. I'm sorry.
It's all right. I'll send you some.
Okay, yeah. So of course, we do take this into account. So what I just wanted to say is that there is still the largest uncertainty in this relation. They come from this radiative corrections. And
this is not a radiative correction. It's a structural correction because the U and the D masses are different. The correction is of order that mass difference squared, but it's of order 10 to the minus 4 in GV squared.
Right. So then when you relate it, to the VUD, then there will be two sources. So one is what the one is talking about, the contribution to GV.
Yes, it's a correction to VUD.
Yeah. Once then when you relate it to the CV plus and VUD, there will be this the effect of GV deviating from 1 that you have to take into account. And then there will be, on top of that, there is an effect of isospin conserving radiative corrections, that you also have to take into account, and this will be encoded in delta RV. And these two effects, of course, are important to relate low energy measurements to VUD. However, the error, that is still dominated, by the imperfect knowledge, of this radiative correction delta RV, rather than the deviations of GV from 1. Okay, so let me go to observables. So again, maybe back to school. Something about the beta decay. So beta decay, again, we have a neutron decaying into electron, neutrino, and then nucleus decaying into electron, neutrino, and another nucleus. And you could, this is a three-body decay, yeah, so you could have, you have the phase space, yeah, you could parameterize it, yeah, by the energy of the outgoing electron or positron, and by the angles of the electron and the neutron momenta, by the directions of the electron neutron momenta in some particular reference frame, which is usually chosen to be with the z-axis along the polarization of the axis of the neutron. So then you can write down the full differential distribution, yeah, for this process, and it will quite generally, yeah, it will have this structure, yeah, that will be pieces, yeah, that contribute to the total, to the lifetime of the nucleus, and those that do not contribute to the lifetime, if you integrate them over the angles, yeah, they will vanish, but they will contribute to so-called correlations, yeah, so you can measure the correlations between the directions of different particles, yeah, so you can measure this so-called little a correlation, which is the correlation of the directions of the electron and the neutrino. You can measure the big A correlation, which is the correlation between the polarization axis and the direction of the electron, and you can also measure the same for the correlation between the polarization axis and the neutrino direction. How do you know neutrino direction? Of course, you never observe a neutrino directly, yeah, in this processes. However, you can measure the momentum of the outgoing the daughter nucleus, and then by momentum conservation you can find what is the what is the momentum of the neutrino. Then there is one more correlation that is never used, never experimentally measured, yeah, and this little c. And then there is a correlation called big D, which is CP violating 1. This is very interesting, but I will. This is measured, and this is a probe of CP violation that, in fundamental physics. However, I will not talk about it in this talk. So I will be assuming that all my parameters in the effective Lagrangians are real, and then this correlation, this decorrelation is 0. So I will be focusing only on those in the first line. And again, so now it's a question, yeah, of simple exercise to connect this correlation and the coefficients, yeah, that I displayed in the previous slide to parameters in the effective Lagrangian. Yeah, this is this CVCS CACT, and this is the so-called all this correlation, all these expressions were derived again almost 100 years ago by Jackson, Trimont, and Wild, yeah, in a seminal paper, and this is something that is calculable, and it's a tedious calculations, yeah, but you can do it, yeah, in a few hours. There is one thing that is one should notice also here is that this correlation that will involve something that I will call mixing parameter, and this is something that we don't know for heavy nucleus decays. So this is a parameter that is specific to each nucleus, and we don't. It will be like a nuisance parameter in our fit because we cannot calculate it from first principles. So now let me tell you just a few words, yeah, about something about the language, that one more piece of the language that is used in beta decays before I go to the data. So when we in particle physics, yeah, when we usually talk about the width, which is the differential width integrated over all the phase space, and this will have this the following form. Yeah, this is there will be the dependence on the effective theory parameters will be hidden in these parameters x and b, yeah, which were defined in the previous slide, and which are functions, yeah, of the Wilson coefficients of the effective Lagrangian, and then there will be a dependence, yeah, on the electron mass and on the Fermi matrix element and so on. And then there is one more thing, yeah, that this width will depend on the phase space. Yeah, so when you calculate the width, yeah, you have to integrate over the electron energy, and there will be some phase space integral that is you take from electron mass to up to the difference of the nucleus mass. So that you take this integral over the available phase space. So this F integral will be very, very different for different nuclei. So in nuclear physics, it's common, yeah, to define a combination of, so somehow to factor out this F and define the combination of F times half-life. Half-life is like lifetime, but with a funny logarithm of 2 factors. So this is another quirk here. So if you multiply the lifetime by F, by this phase space integral, you get something that is independent of the phase space. So it's pretty universal, yeah, for different transitions. And then in nuclear physics, one goes one step further, and also one factors out all this higher order corrections, which are also nucleus dependent. And these you get the expression, yeah, for this big FT, yeah, which is independent, yeah, of this most of this nucleus dependent effects. The nucleus dependent effects remain in X via this this mixing parameter, which is nucleus dependent, and then there is also this integral of phase space integral of m over e, which enters here via the so-called Firth term. Yeah, so. This in this big FT, so big FT is basically the glorified lifetime or glorified width, yeah, with some nucleus transition dependent factors factored out. Okay, so what we know about the data, yeah, so the most important pieces of data are so-called super allowed 0+ to 0+ beta transitions, neutron decay, and neutron decay. So the first piece of data, yeah, is the so-called super allowed beta transitions, and this is the data on the transitions between the nuclei with 0 spin and positive parity. There is many of the transitions of this kind. This is the list of this is the partial list of them, which are the most important ones because their lifetime, or this FT, is measured with the smallest error. So you can see that the error of the measurement, yeah, is on the order of 10 to minus 3 only, and then you have, because you have 15 of those transitions, yeah, you could have if you combine it, yeah, the error goes down to the level of 10 to minus 4. Yeah, so this is a very, very precise measurement. And the importance of this 0+ to 0+ is because you can prove that for 0 spin, the gamma of Teller matrix element is 0. Therefore, this piece dependent on the gamma of Teller matrix element doesn't appear here. The mixing parameter doesn't enter into this transition. So you have much simpler description. You only depend on the vector and scalar interactions. So you directly measure the Wilson coefficients corresponding to vector and scalar interactions. So when you measure when the FT corresponds to you can express FT in this form, as I was discussing in the previous slide. And now this X, this normalization here, is also universal. Yes, it doesn't depend on the nucleus. So the only dependence on the nuclei enters via this Firth term, but is proportional to this little parameter b, which vanishes in the standard model limit. In the standard model limit, there is no scalar interactions. So this term is 0 in the standard model. So in the standard model, you expect that this FT values should be the same universal for all the 0+ to 0+ transitions. And this is indeed what you observe in the experiment. So this is a very strong constraint on new physics. If there were scalar interactions, you would expect the deviations from universality of this FT, but you don't observe any deviations there. There is a perfect agreement between these different measurements in different nuclei. And the very good, because the very good precision, yeah, you're getting a very good constraints, yeah, on the fundamental parameters from this measurement. The second important class of measurements is the neutron decay. So this is a bit simpler, yeah, because there is no nuclei involved, so the theory is simpler. And also this is a Fermi gamma of Teller mixed transition. However, in this case, for the neutron decay, this is the one case where the gamma of telematrix element can be calculated because there is no nuclear physics involved. So this can be calculated in perturbative physics. It's the mixing parameter is equal to minus the square root of 3, and so it's just something that comes out of Feynman diagrams. And again, the data on the neutron decay are very, very precise, also at the level of per mil. And for the neutron, yeah, we have a lot of interesting data. Yeah, so first we measure lifetime of the neutron. This is the latest value, including the latest latest update from the UC and tau experiment. So this is something really very fresh, yeah, from just straight from the oven. You have data on the correlations, yeah, which are also very precise. For example, for the big A correlation, this is this correlation between the magnetic direction of the polarization and the electron. You're getting again the precision that is of the order of 10 to minus 4, very, very, very impressive. And then you have also data with slightly less precise data on the little a correlation and on the neutrino correlation. And this is just some combination of this lambda AB is a combination of A and B. This is also has been measured. So this, you see that since this table is taken from our paper from 2012, but since then there were already 2 important updates. Yeah, so this field of the neutron decay, yeah, is very, 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 very vivid, yeah, and there is a lot of interesting new data coming all the time. So maybe you've heard the story of the neutron lifetime, yeah, that there is a little bit of a mess here, yeah, maybe also some there are apparently some systematic errors involved, maybe a little bit of confirmation bias too. But at the end of the day, hopefully the situation is slowly clarifying. But the one problem, yeah, that we have, yeah, is that if there's 2 main methods, yeah, of measuring neutron lifetime. These are called beam experiments, where you have a beam of neutron and you observe decays of these neutrons into protons, or you have a bottle, so-called bottle measurement. So in very simplification, you just put some number of neutrons in the magnetic trap and you wait and you see how many of them survive after some given time. And these 2 methods give you systematically different answer, yeah, to the question of neutron lifetime. It's very, very likely that there is some systematic problem in this beam measurements, yeah, because the average of the beam measurements disagrees with the average from the bottle measurements by many sigmas. There is some new physics models that are trying to maybe explain it, but this explanations, they don't hold water. Yeah, so this is almost certainly a systematic problem. But also you can see that for bottle measurements itself, there's a big spread. Yeah, so there is also some systematic problem in the bottle measurement itself. Yeah, so you need to take this into account, this inconsistency. What do we do? So PDG has a very nice method, yeah, how to address, yeah, when you how to address this problem of inconsistent measurements. So basically, they have a prescription that you have to blow up the errors of all the experiments. So you basically punish everyone, because there is someone who done wrong, yeah, but you punish everyone. You blow up the error of everyone until you're getting a good chi-squared at the minimum in this case. And this is ad hoc method, but it really reflects that there is some lack of knowledge, yeah, of the true value of the neutron lifetime because of some systematic problems in some experiment. So if you make just the naive combinations of all these results, you would get this green band. But what we do, yeah, is actually we do this combination a la PDG with scaled up errors, and then the 1 sigma error is twice as large. So the so-called S factor is 2.2 for this combination. So we blow up the error because, yeah, so the error is actually larger than the error of the most precise experiment. Yeah, so that's one consequence, yeah, of this a little bit of a mess, yeah, in the neutron lifetime measurement. But yeah, hopefully, yeah, this will converge to one more precise value soon. there is actually, until recently, there has been similar problem with this big A measurement, with this beta asymmetry measurement. So you see, again, you had the older measurements, yeah, that were inconsistent with the newer ones. And again, you had to blow up the errors, yeah, to accommodate all of them. But also, PDG also has a particle data group has an ad hoc procedure, yeah, when to stop blowing up this error. So there is when you should reject this former, less precise, older measurements, and this criteria are now satisfied, yeah. And now when you combine these measurements, you don't have to blow up the errors anymore, and that leads to a very, very precise determination of this big AN parameter. And this transition, yeah, from scaled errors to unscaled errors that only happened a year ago, yeah, and so this is quite a new thing, and thanks to that you get a reduction of the error by a factor of 5, yeah, which is quite impressive. There is more data on nuclear decays, yeah, that we also use in our feed, yeah, but they are in practice there are measurements of correlations in various nuclei. There's also measurements of beta polarizations in ratios, yeah, in nuclei. They are precise, but they are less precise than the two classes we discussed before. So in practice, yeah, they have little impact on the global feeds now. And then there is another class of decays, yeah, which we actually was for the first time we included in the new physics analysis, that they were included only in this paper, yeah, by in last year. These are the so-called mirror beta decays. So mirror beta transitions, yeah, are transitions between isospin half, same spin, positive parity nuclei. They do depend on the mixing parameter rho. So there is this nuisance parameter in your feed that you don't know from first principles. However, in this case, various higher order corrections can be estimated in to a good precision. Yeah. So in the mirror beta transitions are the ones that where you have the for example, you have a nucleus with 5 neutrons and or 5 protons and 4 neutrons that turns into a nucleus with 5 neutrons and 4 protons turns into a 5 protons and 4 neutrons, or vice versa. Yeah. So you just have the mother, the parent, and the daughter nucleus are sort of mirror reflections in isospin of each other, and that thanks to that there is a better control, yeah, of various systematic and derivative corrections. So this is the list of various mirror beta transitions. Maybe the most well known is the tritium decay. This is an example of the mirror beta transition. You have 2 neutrons and 1 proton, and it decays into a nucleus, a helium nucleus, yeah, with 2 protons and 1 neutron. But yeah, then again, the list is much longer, yeah, of those. Yeah, so this is the list from old papers. So these values of the lifetime are not, they are not the latest one. Yeah, this is just for illustration here. And you can see that in this case, FT value, yeah, is different for different nuclei, yeah, because now you have this piece, this mixing parameter, yeah, that is breaking the universality of FT. However, if you only measure the lifetime, yeah, so you don't learn anything actually interesting about fundamental parameters, because you have this nuisance parameter rho. So when you, let's say, if you determine this Wilson coefficients from other processes, this measurement of the lifetime only gives you the measurement of the mixing parameter rho, which is maybe interesting from the point of view of nuclear theory, but from the point of view of fundamental physics, it's less interesting. So you need something more input, more information, yeah, that will allow you to factor out this mixing parameter. And fortunately, for a smaller subset of mirror transitions, which is decay of fluorium, neon, sodium, potassium, argon, and this. You also have an information from the correlations, which is precise enough so that you can determine mixing parameter from this correlation measurement, and then together with the lifetime measurement, with the FT measurement, you're actually constraining fundamental parameters. So in this paper from last year, yeah, we used all this data, yeah, to in the fit, yeah. And so let me go to results, yeah, and let me start with the standard model case, yeah. So this is my effective Lagrangian, and in the standard model limit, this values, yeah, of CS, CV, CS, and all the ones corresponding to the right-handed neutrinos, they are 0. In the standard model limit, there is only 2 Wilson coefficients in this effective Lagrangian that are non-zero. This is the CV plus and CA plus, and yeah, they correspond to Fermi and Gamow-Teller beta transitions. So if we put all this data into the fit, yeah, this is the answer for the measurement of CV and CA that we obtain. And what I want you to notice here, yeah, so the values of these parameters are order 1 in the units of 1 over v squared, yeah. So these are dimensional parameters. So and they are order 1 in the units of 1 over v squared, because the bulk of their contribution comes from integrating out the W boson. However, the error, yeah, that is really impressive, yeah. So the error for this determination is of the order of 10 to minus 4 in the standard model limit. And also this big fit also gives you information about the mixing parameters of the mirror nuclei, because these are nuisance parameters in our fit. But when you want to fit all the data, yeah, you will also get information about this, yeah. And they are also measured at the level of 10 to minus 3. This doesn't tell us anything about fundamental physics, yeah, but this is some interesting information, yeah, for nuclear theory. So, but now we want to translate this measurement into the fundamental parameters. So here is the expression, yeah. So we have CV plus and CA plus, yeah. They are related to the VUD parameter in the standard model and to the GA parameter, yeah. And GA is the axial charge of the neutron. So this is some QCD parameter, yeah, from strong interaction. And then when you assuming the standard model hypothesis, yeah, you're getting a determination of VUD and GA at the 10 to minus 4 with a 10 to minus 4 precision, yeah. So the error is for the VUD is 2 times 10 to minus 4, yeah. So this is amazing precision. Given that it comes from nuclear physics. Usually we don't think about the nuclear physics in this as precision measurements, but in this case, yeah, the precision is really impressive. And of course, this is the most precise determination of VUD. All other determinations of VUD from non-nuclear physics, yeah, they will be less precise. So this is our best source of information about the VUD matrix element in the standard model. The same goes for the GA. So that was, I think, the question, yeah, of Anthony before, yeah, if you assume the standard model, you can determine GA from experiment, yeah, with the precision that is better, that is of the order of 4 times 10 to minus 4. So again, very impressive. This is some non-perturbative parameter that can be calculated on the lattice, but only with 1% precision. So what about VUD measurements? Yeah, so maybe you heard a little bit about the story, yeah, but there was some seismic shift recently in this because the determination of this radiative correction that was due to Marciano and Sirlin in an old paper 2006 that was challenged by a newer paper by Seng et al., which led to the change in the determination of VUD from determination of VUD, which takes it away from the value that you would get assuming unitarity of the CKM matrix and the VUS measurements in K-on decays. So this is what you would expect from unitarity, and this is what you get, and there is some tension between the two. So since then, there were different new calculations of these radiative corrections that basically confirmed, yeah, this new values. Our error that we use here is slightly larger because it also involves additional sources of uncertainties in super allowed 0+2 0+ beta decays that were determined in the series of paper by Seng et al. And Goldstein. So the error that we have is slightly larger, which leads to a slightly less tension, yeah, with unitarity. So the tension in our fit is only at the level of 2 sigma, yeah. So it's not as large as some papers claim. Now, what is it? Maybe this is the plot that I took from a Twitter feed of Martin Gonzalez Alonso. Yeah, so if you want to know the latest news, yeah, in this nuclear beta transitions, yeah, this is the Twitter feed. Yeah, is a very good source. So where does this tension come from? And actually, the tension comes mostly from super allowed beta transitions, from the 0+ to 0+. If you look at the other groups of observables, like the neutron decay, mirror decay, and the pion decay, they don't have any. They don't lead to any tension with unitarity by itself. Especially this interesting story of the neutron decay. So if you're taking this actually determination of VUD from neutron decay, this a little bit depends on how you combine the data, whether you scale errors or not. But it's interesting to notice that if you take the most precise measurement of neutron lifetime and of big A correlation, which gives you the GA, then the new value, especially when you include this the latest measurement from UCN, is perfectly consistent with unitarity, and the error is only a factor of 2 larger, yeah, than the one from super allowed decay. So it seems that the newer data from neutron decay, they solve the problem of CKM unitarity in the sense that they are consistent with CKM unitarity. And it looks like there is some systematic problem, yeah, with super allowed beta decays. Like maybe still some errors are systematic errors in these transitions have been underestimated. In fact, if you look at the goodness of fit of the super allowed beta decays, is actually you have 15 different transitions, but the chi-squared at the minimum is only of the order of 6. So there is some suggestions, yeah, that there is some overfitting that have been done in the 0+ to 0+ transitions, and this is what apparently causes the CKM unitarity problem. But with the newer data, the CKM unitary problem seems to be going away. Yeah, so that's the message, yeah, of this plot. So just okay. So I'm already towards the end. Yeah. So I will let me tell you finally about the main topic of this talk. Yeah. What about the constraints on new physics? So now we take the we take the effective Lagrangian, yeah, with the CV and CA plus parameters, but now we also allow for scalar and tensor interactions. And then we have enough data, we have enough precise data to determine all 4 of these parameters at the same time. So we're still getting a very precise measurement of this standard model parameters, CV and CA. But in addition, simultaneously, we're also getting a constraint on the scalar and tensor interaction, which is totally modeling dependent in the sense that this is a big likelihood with some correlation, so some correlation matrix, and this constraint they hold, assuming all of these 4 Wilson coefficients are present at the same time. So you can from this you can reconstruct the likelihood, yeah, and you can constrain any specific model. And you see that the constraint of the scalar and tensor interactions are at the level of 10 to minus 3. So this is again a very strong constraint on new physics, and there is no preference for new physics. Yeah, so in a sense that the value of the scalar and tensor Wilson coefficients are consistent with 0. So now, what does it mean about fundamental parameters? Yeah, so here I repeat the map that I showed you before. And you see that CV and CA are connected to this left-handed and right-handed interactions at the quark level, and CT and CS are connected to the tensor and scalar interactions at the quark level. So there is now you see that in this map mixes new physics and standard model parameters. So in the presence of the new physics, for example, you don't measure VUD anymore. You measure VUD that is multiplied by this epsilon L, epsilon R parameters that are new physics contributions to vector left-handed and right-handed vector interactions between the leptons and quarks. So you don't no longer have access to VUD. You only measure this polluted VUD, and that means that polluted VUD doesn't have to satisfy the unitarity of this. I mean, this is not an element of the unitary CKM matrix, so it doesn't have to be connected to VUS. So in principle, yeah, there can be a deviation. You can interpret a possible deviation between the measurement of VUS and the measurement of VUD as being due to this new physics contributions polluting your observable. The same is true for the axial charge. Yeah, you don't measure axial charge. You measure a combination of this GA hat, yeah, of the true axial charge and some new physics parameter. Approximately what you measure is axial charge shifted by contribution due to right-handed interactions. So now you cannot, in the presence of new physics, you don't know what the GA is. Yeah, you only measure a combination of GA and epsilon R, which means that if you want to disentangle the epsilon R and GA, yeah, you have to insert the information about the GA, the true GA from lattice, and if you insert this, you have in the fit, yeah, we will insert this value from the lattice, but which is, however, known only with the 1% precision. So this is the importance, yeah, here of the lattice determination of GA. From the point of view of new physics, it allows us to obtain a constraint on the right-handed interactions, yeah, that are parameterized by this epsilon R. So when we do this fit, yeah, this is what we get. Again, we're getting a constraint on this polluted VUD, but now with the 10 to minus 4 times 10 to minus, so the error is twice as large as in the standard model fit, but it's still impressive. We're getting a 1% level constraint on the epsilon R, even though the data are per mil level, yeah, but because we have to insert this lattice information, which is only 1% level precision, we're getting this only 1% level constraint epsilon R. On the other hand, for epsilon S and epsilon T, the scalar and tensor interaction, those that can come from leptoquarks, yeah, for example, we're getting a constraint at the level of 10 to minus 3, which if you translate it into a new physics reach, yeah, so this is what you get. In assuming strongly coupled new physics, yeah, at high scale, the scalar and tensor interaction, they can, this epsilon S and epsilon T, they can probe new physics up to 100 TeV. So if you have a 100 TeV strongly coupled leptoquark at 100 TeV, it would now show up in the measurement. I mean, it is now excluded by the measurements in nuclear physics. Epsilon R, for epsilon R, you're getting slightly lower reach because of the reasons that I discussed. And epsilon P, you don't constrain from nuclear physics, but you do constrain it from pion decays, and getting even better constraint because of so-called chiral enhancement. I will not go into that. And you go into up to PeV scale, yeah, probing new physics. And this propaganda message here, yeah, is that this precision, yeah, is much better, yeah, than what you get directly from the LHC, and it's comparable what you get indirectly from the LHC. If you're looking at the Drell-Yan processes, proton-proton goes into a pair of electrons or electron-neutrino, or pair of muons or muon-neutrinos. You can probe the same interactions between the quarks and leptons, and you're getting constraints that are comparable to those from nuclear physics. Yeah, so in this sense, the LHC and nuclear physics, yeah, are complementary and competitive. Okay, sorry, I went over time, and I think I should. Yeah, there is a little bit of other fits that I wanted to discuss. Yeah, but maybe let me stop here. Yeah, and at the summary, and just that this nuclear physics is a real treasure trove for constraining both the standard model and the physics beyond the standard model. And we are getting, we are now at the technological level that we can combine all this information from different beta transitions and summarize them into a very compact form as a fit on the Wilson coefficients of effective Lagrangians. And we have this constraints on the Wilson coefficient of the whole ladder of effective Lagrangians, stretching from the low energy scales of few MeV up to high scales above the electroweak scale. Thank you very much.
Yeah, thank you very much, Adam, for a very interesting talk. So we have time for questions. Who would like to go first?
I have a question, if you don't mind.
Of course.
So going back to the unitarity issue and the super allowed transitions, you presented a speculation about what might be going wrong with the super allowed transitions, but I didn't quite get it. Could you go?
No, sorry. Okay, so first speculations about what is going wrong. Yeah, so you see that this combination, yeah, of super allowed beta transition, yeah, is done by two huge experts in this field, Hardy and Tauner. They've been doing this combination for the last I think 20 or 30 years. Yeah, every 5 years, yeah, they present an update of this measurements. Yeah, so this is huge work done. My speculation, yeah, is that it's not a speculation. It's just when I looked at the data, it looks to me naively from the statistical point of view that they are too consistent with each other. Yeah, so you have 15 measurements, and the scatter of these measurements is much smaller than what you would expect from pure statistics.
Mm.
This is the only thing I can say. I cannot say that they made an error here or here, or they're using this. Okay, in the field, these papers are often criticized, yeah, for underestimating errors, but that are due to that are related to some very complicated nuclear structure corrections yet for which, but I have no competence, yeah, to actually comment on that. Yeah, so all I can say, yeah, is that only from the statistical point of view, the data, all these 15 data points, they look too consistent with each other.
Okay, thanks. Interesting.
Yeah.
I had a thought about that as well. I mean, the number that you quote is really quite mild by the standards of overfitting, and there's another interpretation that there is consistent overestimation of systematic errors or of errors generally in the measurement, and it would not be the first time that people have done that, and that sort of tends in the other direction.
Right. So we are just want to comment here that we are using larger systematics, yeah, than most of the groups, yeah, and we are so our error bars is about I don't know 50% larger, yeah, than you can find in other papers, yeah, because we are including like some very, very latest systematic effects, yeah, that were discussed in the papers a year ago, but yeah, it is possible, yeah, that there is still larger systematic effects, yeah, that haven't been included and that they have.
No, sorry, my point was the opposite one, was that was a counter argument to your overfitting argument is that if the results are too good, the agreement of the results is too good based on their facial errors, then an interpretation is that the errors have been overestimated by the authors. In experimental particle physics, that happens on a fairly regular basis, and that is unfavourable for your idea that the tension can be made to go away. So.
No. So okay, so I understand your point, yeah, and I agree. You could look at it this way, yeah. But you have to know that these numbers, yeah, this is not something that comes directly from measurement, yeah. So what is measured, yeah, is the lifetime or half-life of a nucleus, and then it has to go through some machinery that you have to change this half-life into this FT parameter and subtract various corrections, yeah. And I think that when you choose how to subtract this nuclear physics corrections, it's possible that some the choice of the model was done in such a way as to get this agreement, and then you see that this agreement is actually too good, yeah, to be true. That there is some problem, yeah, in this procedure, yeah, because the consistency between these different measurements is too good, yeah. So there's a lot of things that goes into the sausage, yeah, to give this 15. It's not.
You're saying that the measurements may be herded. You're saying the calculations, there may be some herding in the calculations. That's your
yeah. So the point is that there is a lot of tweaking. Yeah. So some of this corrections, they come from nuclear physics models. Yeah, but there is several nuclear physics models, and then there is a choice. Okay, I choose this model as to describe these corrections, and I reject those models. And I think that
express a view, but I understand the point.
Yeah. So what happens is here is not overfitting but over tweaking. Yeah, and that's a possibility. But of course, I'm not an expert in this. Yeah, so I cannot put my finger. Oh, you did it wrong. Yeah, you should do it differently. Yeah, I'm not an expert in this field.
Thank you.
Tony has a question. Do you want to?
Yes, I hope you can hear me now.
Yes.
I wanted to follow up because I didn't explain my comment earlier. The VUD is the coupling is the transition at the quark level.
Mm-hmm.
The matrix element for the transition neutron to proton is no longer 1 because the U and D quark masses are different. The correction is of order that mass difference squared. But that matrix element squared deviates from 1 by about 1.2 by 10 to the minus 4. So at the level you're starting to compare unitarity with experiment, that correction is no longer negligible. So there should be basically an increase in VUD squared deduced from experiment by about 1.2 by 10 to the minus 4.
Mm-hmm. But you see, this, so the error currently is two times.
Yeah, so it's about a quarter of that current error.
That would be
which is no longer negligible, and if the value gets better, it will start to be important.
Yeah, I agree.
True. I guess one has to include it in the future there. Can I ask one more question? So you compared it to other constraints, in particularly LHC. Was that kind of current LHC constraints, or is that kind of prospective sensitivities?
No, I would say it's a current. Yeah, so for the current, LHC constraints, you get also a constraint on this epsilon s and epsilon t at the level of 10 to minus 3. Yeah, so and the same for epsilon r. I think you can go asymptotically with LHC not high luminosity to the level of 10 to minus 4. Yeah, so that should be a goal for the LHC. So you would get somewhere here. Yeah, so there will be a little bit for nuclear physics to catch up, but I think in this 10 years also there will be progress. Yeah, in the neutron decay, and you will also get progress from nuclear physics. Yeah, so the goal of this plot is to show that they're really going head to head. Yeah, there's two complementary sources of information about the same kind of decays, the same kind of interactions between the quarks and leptons.
Okay, so that's basically both current and now basically future. Okay, one has to see them.
Sorry, I see that there is something in chat. Is it something?
Yeah. So I think maybe it's move it over time. Let's thank Adam once more because some people have to leave. But so thank you very much once more, Adam. But if you have more questions,
so I think both currently and both in you will.
Yeah. So I think people may still have more questions. I just thought